In this chapter, what we are going to see is stability analysis and root locus techniques. Stability analysis and root locus technique. Here, this x1 of t is output, x-axis is time, y-axis is output, x1 of t. The output is decreases, finally settles at 0. So this signal can be called as bounded signal. It has limits. Within that limits, so bounded signal. A step signal, if you take up to infinity, it is within that bounded signal. A sinusoidal signal with constant amplitude, again bounded signal. Here, e power at, if you take, this is e power at, go on increases, exponentially increases. This is unbounded signal. It will go to infinity. This will go to minus infinity, minus e power at. This will go to minus infinity. This is unbounded signal. We see that this is sinusoidal signal, but its amplitude go on increases. E power at sin omega t. E power at sin omega t. Its amplitude go on increases. Unbounded signal. Again, unbounded signal. So these are all examples for unbounded signal. If the output of the system is unbounded, then the system is unstable. If the output of the system is unbounded, if you plot the output of a system, it is looking like this. This is output of a system. Its output is plotted. It looks like this. This is an unstable system. This is marginally stable because it is neither settles nor increases. Marginally stable. This is stable system. This is stable system. This is unstable system. Unstable. Stable. Stable. Marginally stable. Unstable. If the system's output is like this, the system output is like this, we can say that this is stable system output. This is stable system output. This is marginally stable output. The system has marginally stable output. This is unstable output. This is also unstable output. Our system itself unstable. System itself, that's why it gives unstable output. The system is unstable, that's why it gives unstable output. In other words, the system is unstable, that's why it gives unbounded output. We must say like that, unbounded. It is not bounded signal, unbounded. Unbounded output. Unbounded output. Unstable system gives unbounded output. Then what is the definition for stability? If we give you a bounded input, we know what is bounded input signal. What should be how it should look like. Bounded input signal is given. The output also should be bounded. Then the system is said to be BIBO stable. Then the system is said to be BIBO stable. Bounded input, bounded output stability. The system is said to be bounded input, bounded output stable. A stable system, for that I am giving bounded input, it gives bounded output. Then the system is said to be stable. I am having an unstable system. For that I am giving bounded input, it gives unbounded output. Because the system is unstable system. The system is unstable system. That's why for a bounded input signal, it gives unbounded output. Unbounded output. Therefore, it is an unstable system. bounded for an engineer, what is bounded input? I'm not talking about signal. What is bounded input? All for mathematician, if it is not infinity, then it is called bounded. If it is less than infinity, mathematician will say that bounded. What is bounded signal? Bounded signal means he will say if it is less than infinity, then it is bounded. He can say. But for an engineer, how you can say it is bounded signal, bounded input? All measurable inputs are bounded inputs. All measurable. If it is infinity, we cannot measure. So all measurable inputs are bounded inputs. If the output also measurable, then it is bounded output. So for a bounded input, the output also bounded means it is a stable system. For a bounded input, if the system gives unbounded output, then it is said to be unstable system. Mathematically, how we can explain BI/BO stability? What is C of S? C of S equal to input is R of S. Therefore, I can say that G of S, R of S. Because R of S is input, C of S, G of S is the system. That's why C of S, output equal to G of S multiplied by R of S. What is C of T? Multiplication in frequency domain is convolution in time domain. Convolution in time domain. That's why we can say 0 to T. 0 to steady state value means infinity we have put. So let us put infinity. R of, G of T, G of tau, R of T minus tau, D tau. Convolution in time domain. Convolution in time domain. What is BI/BO stability? Bounded input. R of T minus tau is bounded. R of T minus tau is bounded. That is R of T is less than M, less than infinity. It is measurable quantity, M. R of T is measurable, bounded input. Therefore, what I can write is if C of T, modulus of C of T equal to modulus of C of T equal to modulus of integral of 0 to infinity G of tau R of T minus tau D tau. This must be less than infinity. It must be less than M, less than infinity. Then it is said to be bounded. The system is said to be bounded. The final output must be less than infinity, measurable quantity. But we know that R of T is bounded, that is less than M. So we can say that it is less than or equal to integral of 0 to infinity modulus of G of tau modulus of R of T minus tau T tau. This we know mathematically. Inequality equation. If modulus is breaking down, then it must be less than or equal to G of tau R of T minus tau D tau. Or we can say that less than or equal to, this can be replaced by M because it is less than M. R of T is less than M. So it can be replaced by M. Therefore, M integral of 0 to infinity modulus of G of tau D tau. You can say like that. If when this will be measurable, M is measurable already. M is already measurable. If this is also measurable, if this is also measurable, then the entire quantity C of T is measurable. C of T is measurable. If this is measurable, this is bounded, then C of T is bounded. What is this? The integral of 0 to infinity G of tau D tau is, what is this? It is this is nothing but impulse response. This is nothing but impulse response. It is nothing but impulse response. What is impulse response? R of S equal to what? For impulse input, R of S equal to 1, R of T equal to del of T. For R of T equal to impulse input, then R of S equal to 1. For that, it is integral of 0 to infinity del of T. Let us assume that in that case, M becomes 1. M becomes 1. So this becomes this modulus of C of T must be less than or equal to this. It means this impulse response must be bounded. Impulse response must be bounded, or integral of G of T dt must be bounded. Integral of, both are same. Integral of G of T dt must be bounded for a stable system. For a stable system. In frequency domain, we need not check for BIBU stability. We need not check integral of G of tau d2. We check where is the location of poles. Where is the location of poles? If it is on the left-hand side, we can say that the system is stable. If it is on the left-hand side, we can say, if the poles are in the left-hand side, we can say that the system is stable. Therefore, we must know what is poles. Already we have seen a review of poles and zeros. Poles, what are poles? Poles are roots of denominator polynomial. In other words, suppose D of S is the denominator polynomial, equate to 0, find the roots. That is called poles. What is zeros? N of S is the numerator polynomial, equate to 0, find the roots. These are all zeros. The zeros of system are roots of the numerator polynomial. So if poles are in the left-hand side of S plane, this is S plane, this is S plane. If the poles are in the left-hand side, then the system is said to be stable. If the poles are on the right-hand side, system is unstable. Poles on the right-hand side. But zeros can be on the right-hand side. How zeros are represented? Suppose I am having 1 0 here, 1 0 here. Zeros are represented by circle. I am having 1 0 here, 1 0 here. So definitely a complex conjugate will be there. 0 will be represented like this. Poles will be represented by cross. Pole is represented by this. 0 is represented by this. This is another 0. This is another 0. Zeros are represented by dot and circle. Poles are represented by X. Poles are represented by X. So if the poles are on the left-hand side, then the system is said to be stable. Find the poles and zeros of the transfer function and plot on a S plane. Find the pole. Poles are -4, one pole. Then another pole is -6 plus or minus square root of 4AC divided by 2A. -4 4J -3 plus or minus 4J. So these are the poles. Zeros are -1, -2, -1, -2. In a S plane. So -4 at this point, one pole. Another pole is -3, -4. So -3, -4. Here one pole. So here one pole. Zeros are at -1, -2. This is called the pole zero plot. Pole zero plot. Find the poles and zeros of the transformation. Sketch the pole zero plot of the system. Another system. Here, the poles are 0, 0, minus b plus or minus square root of b square minus 4ac. Divided by 2a. So what are the poles? 0, 0, minus 2, minus 3. Zeros are -1. So what is the plot? -1, -2, -3, sigma j omega. Here the -1, 0 is there. At a -2, one pole. At a -3, one pole. This is asked how to represent repeated poles. At 0, 2 poles are there. One pole means you can put like this. How to represent second pole? We have to draw like this. 2 poles are there. Here, repeated poles. 2 poles. 2 poles are there. We have to mark like this. That's why this is. Other poles are simple. So repeated poles has to be marked like this. Why the system becomes unstable? Because pole on the left hand side means, suppose I am having a system with S plus A. A by S plus A is the system. If you take an impulse response, G of S equal to this. R of S equal to 1. What is impulse response? Impulse means what? Hammer blow. That is R of S equal to 1. For that, what is the output? C of S equal to G of S multiplied by R of S. G of S multiplied by R of S. That is equal to A upon S plus A. A upon S plus A. That is equal to C of T equal to what? We have to take Laplace inverse. A e power minus AT. If it is in the left hand side, you will get e power minus AT. If it is A by S minus A, what you will get? C of T equal to A e power plus AT. Plus AT means what is the response? The response go on increases. Unstable. That's why this pole must be on the left hand side. Here, what is the response? It comes like this. This is A e power minus AT. This is A e power plus AT. Go on increases. That's why pole must be on the left hand side. Here, the pole is on the left hand side. The pole is on the left hand side. The response you see bounded. Here, the pole is on the right hand side. You see that go on increases, unbounded. Here, the pole is at the origin. What is the response? Step out. 1 by S. The system is 1 by S or A by S. A by S. Impulse response is step out. Here, magnitude bounded. Magnitude bounded. But if you see the energy, if you integrate up to infinity, energy becomes infinity. Energy becomes infinity. If the magnitude is bounded, then we can say the system is stable. These are all what we have taken is real poles. Real poles, no oscillation. If we take a complex pole, 2 poles are there, second order system, left hand side, it oscillates, but finally for impulse input, all are for impulse input, not step. Impulse input. Impulse input means giving a blow, giving a punch, that's all. After that, initially it's rest. If we give punch, oscillates, finally it comes to rest. So it oscillates, finally it comes to rest. So it is stable system. Here, the poles are on the right hand side. If we give a punch, what will happen? Its amplitude go on increases. Unstable system, unbounded output. Unbounded output. This is bounded output. Bounded output. Here, always oscillating. The poles are exactly on the J omega axis. The S plane, these are all S plane. This is also S plane. S plane. Poles are exactly on the J omega axis. Sustained oscillation. This is called marginally stable. Marginally stable. Suppose I'm having 2 poles, repeated poles at the axis. Repeated poles on the J omega axis. Then also it is unstable. If 1 pole is on the J omega axis, no problem. Marginally stable. Oscillation, marginally stable. If repeated poles are there means, then it is unstable. Unstable. Repeated poles. That's why amplitude go on increases. Amplitude go on increases. All are impulse responses. All are impulse responses. All are impulse responses. Means R of S equal to 1, not 1 by S. So if the roots are in the left half of S plane, integral of 0 to infinity G after dt will have a finite value. The system response will comes to 0. The system is stable. The roots of the characteristic equation lie in the left half of S plane. Then stable system. The roots have positive real part. Positive real part. That is the right hand side. Its the integral of G of tau d tau is infinite. Unstable. Non-repeated roots on the J omega axis. Non-repeated roots on the J omega axis means sustained oscillating. It will oscillate forever without increasing amplitude. That is called marginally stable. That is called marginally stable. If repeated roots means unstable, unbounded output, unstable. Unstable. Repeated roots on the J omega axis. Repeated roots on the J omega axis, unstable. This do it yourself. Discuss the stability of the following system. Check the note down, and check the stability of these systems. Good morning to you all. Already we know that the poles, any one of the pole is on the right hand side of the S plane, then the system is said to be unstable. We know. Already we have seen for first order, second order, up to third order we have seen. We know how to find the poles of first order, second order, up to third order. But beyond that, it's very difficult to find the roots of denominator, that is poles of the system. That's why it's difficult to say the location of poles. So there is a procedure to find the location of poles, whether it is on the right hand side or left hand side or on the j omega axis. For that, there is a criterion called Routh-Hurwitz criterion. Let us see that. Routh-Hurwitz criterion says that the first column of Routh array can say the location of poles. If any of the first column elements, any of the first column elements have sign change, then the number of poles on the right hand side equal to number of sign changes in the first column of Routh array. Routh array is an array of numbers formed from the characteristic polynomial. Suppose it is like matrix, the first column of Routh array doesn't have any sign change, means then the system is said to be stable. Now we will see. Routh array. Let us form the Routh array. Let f of s, that is characteristic polynomial, equal to s power n, a n s power n plus a n minus 1, s power n minus 1 plus a n minus 2, s power n minus 2 plus etc. plus a1 s power 1 plus a naught. Be a nth order characteristic polynomial, or we can say that denominator polynomial of a open loop system or closed loop system. If you find for open loop system, then it is called open loop stable system. If you find for closed loop system, if you find the closed loop poles for a closed loop system, then it is called closed loop stable system. This is the given characteristic polynomial or denominator polynomial. It is nth order. Nth order. Because s power 5, that's why nth order. How many poles will be there? N number of poles will be there. To find whether the poles are on the right hand side or not, we have to form Routh array. Routh array. How to form Routh array? The highest degree we have to write s power n, s power n minus 1, s power n minus 2, s power n minus 3, etc. s power 0, s power 1. S power n means we have to write a n here. Next coefficient a n minus 1. The next coefficient is a n minus 2, a n minus 3, etc. A naught. So if it ends here, then we can put a 0 here. Otherwise, sometimes it may end like this, a1, a naught like this. It depends upon number of even number of coefficients, means it will end like this, a1, a naught. Odd number of coefficients means it will end like this. So from the polynomial, now we can form two rows. First row is an minus 2, etc. a naught. Second row is an minus 1, an minus 3, etc. So this is first row of Routh array. This is second row of Routh array. Now we have to form third row, that is bn minus 1, etc. etc. Up to b1 it will come. One short of the polynomial. So what is bn? Bn equal to an minus 1 multiplied by an minus 2 minus an multiplied by an minus 3 whole divided by an minus 1. This we have to remember this way. We have to multiply these two minus product of these two divided by this. That is bn. What is bn minus 1? Bn minus 1 equal to, again we have to consider an minus 1. Here what will be the number? An minus 4. Here an minus 5. So what is bn minus 1? Bn minus 1 equal to an multiplied by, an minus 1, same element, n minus 1 multiplied by an minus 4 minus an multiplied by an minus 5 divided by an minus 1. That is bn minus 1. Here, how we found bn? We are taking these four elements and we have to multiply second row first column element with the second column first element minus first column first element multiplied by second column second element divided by an minus 1. How we will find the determinant? Suppose I am having a matrix 1, 2, 3, 4. For that, how we will find a determinant? 1 multiplied by 4 minus 3 multiplied by 2. Here we are doing in the opposite way. We are multiplying 3 multiplied by 2 minus 1 multiplied by 4 divided by 3. Just opposite to determinant. So how to find the next element? Bn minus 2, that is equal to again an minus 1. The same element we have to take. Next element is an minus 6. Here an minus 7 multiplied by an minus 6 minus an multiplied by an minus 7 whole divided by an minus 1, etc. You will get, suppose here in the first row, 8 elements are there, means here in the third row you will get only 7 elements. Here suppose 7 elements are there, means here you will get 6 elements, like that. One short of first row you will get. Then next row how to form? Cn minus 1, etc. C2, up to C2 it will come. How to find Cn? Cn equal to, we have to take second row and third row we have to take. Just now we found the third row. To find fourth row, this is fourth row. This is first row. Second row. Third row. To find third row, we used first row and second row. To find fourth row, we have to use second row and third row. Same procedure. Cn equal to Bn multiplied by an minus 3 minus an minus 1 multiplied by bn minus 1. Bn minus 1 divided by bn. That's all. The same way. So to find Cn, what we have to do is Bn multiplied by An minus 3 minus An minus 1 multiplied by Bn minus 1 divided by Bn. That way we can find up to S power 0. S power 0. Then what we have to do is, we have to check, is there any sign change in the first column of Routh-Array? If no sign change in the first column of Routh-Array, then the system has all poles in the left hand side of S plane and stable. Otherwise unstable. Good morning to you all. Already we know that the poles, any one of the pole is on the right hand side of the S plane, then the system is said to be unstable. We know. Already we have seen for first order, second order, up to third order we have seen. We know how to find the poles of first order, second order, up to third order. But beyond that, it's very difficult to find the roots of denominator, that is poles of the system. That's why it's difficult to say the location of poles. So there is a procedure to find the location of poles, whether it is on the right hand side or left hand side or on the j omega axis. For that, there is a criterion called Routh-Hurwitz criterion. Let us see that. Let us see one example. Determine the stability of the system with the closed loop transfer function C of S upon R of S. C of S upon R of S. C of S upon R of S 10 upon S power 6, 2 S power 5 plus 2 S power 4 plus 3 S cube plus 5 S square plus 6 S plus 1. Sixth order system. Number of poles 6. So we have to find the location of poles. S power 6, S power 5, S power 4, S cube, S square, S power 1, S power 0. 7 rows we have to find. First 2 rows we can obtain from the polynomial. Denominator polynomial. 1, 2, 2, 3, 1, 2, 5, and 1 are in the first row. Second row, 2, 3, 6. 2, 3, 6. These are all in the second row. Now we have to find the third row. Third row, let it be A, B, C. C, first element of C. C, first element of C equal to 2 by 2, 4 minus 1 by 3. 3 divided by 2. That is 1 by 2. So we can write 1 by 2. The next element is C2 equal to 2 multiplied by 5, 10 minus 1 multiplied by 6, 2 multiplied by 5, 1 multiplied by 6 divided by 2. That is 4 by 2 equal to 2. Therefore, second element is 2. The next element is 2 multiplied by 1. C3 equal to 2 multiplied by 1 minus 1 multiplied by 0 divided by 2. That is equal to 2 by 2 equal to 1. The same element we are getting here. So third row is over. What is fourth row? D1 equal to 1 by 2 multiplied by 3 minus 1 by 2 multiplied by 3 minus 2 by 2 whole divided by 1 by 2. That is equal to 1.5 minus 4 divided by 1 by 2. That is equal to 2.5 multiplied by 2 equal to 5. Minus 5. Minus 5. That is equal to minus 5. Minus 5. Next element is D2 equal to 1 by 2 multiplied by 6. 1 by 2 multiplied by 6 minus 2 by 1. 2 multiplied by 1 divided by 1 by 2. That is equal to 3 minus 2 divided by 1 by 2. That is equal to 2. The next element is, here 0 is there, that's why no next element. Then E1 equal to minus 5 multiplied by 2 minus 1 by 2 multiplied by 2. That is whole divided by minus 5. That is equal to minus 10 minus 1 divided by minus 5. That is minus 11 by minus 5. That is equal to 11 by 5. So what you will get is 11 by 5 you will get. Then next element is minus 5 multiplied by 1. This is 0. So you will get E2 equal to minus 5 multiplied by 1 minus 1 by 2 multiplied by 0 whole divided by minus 5. That is equal to 1. So 1 you will get. S power 1, that is equal to, we have to find 11 by 5. F row F1 equal to 11 by 5 multiplied by 2 minus 5 by 1 whole divided by 11 by 5. That is equal to 22 by 5 plus 25 by 5 whole divided by 11 by 5. That is equal to 47 divided by 11. Therefore, next element is 47 divided by 11. Here only 47 by 11 multiplied by 1. G element. 47 by 11 multiplied by 1 minus here 0. 5 multiplied by 0. Therefore, you will get to the 1, the same one here. So all elements we found. How many sign changes? How many sign changes in the first column? These are all first column elements. If you go from A to B, no sign change. A to B, A row to B row, there is no sign change. No change. B to C, when you transfer from B to C, there is a one sign change. No sign change. No change. From C to D, If you travel from C to D, one sign change. That is positive to negative. Positive to negative. So from D to E, if we travel -5 to +11/5. Therefore, one sign change. Again, one sign change. Then E to F, no sign change. E is positive, F also positive. Then F to G, no sign change. Therefore, the total number of sign changes is equal to 2 sign changes. That is from positive to negative, then negative to positive. Therefore, 2 sign changes. 2 sign changes. Therefore, two poles on the right hand side, and hence the system is unstable. System is unstable. Now let us check in MATLAB. MATLAB window, we can find the roots of the 6th order polynomial by calling the function called roots, and we have to pass the parameters. We have to pass the parameters. The roots. We have to pass the parameters. The parameters are 1, 2, coefficients. Coefficients are 1, 2, 3, 5, 6, and 1. That's all. So, as a row of elements, we have to pass to roots. Immediately, it gives the roots. You see that only 2 roots having positive real part. Only 2 roots have positive real parts. The remaining 4 has negative real parts. Therefore, 2 roots on the right hand side. 2 roots on the right hand side. What we found in Routh-Hurwitz is correct. Good morning to you all. Already we know that the poles, any one of the pole is on the right hand side of the S-plane, then the system is said to be unstable. We know. Already we have seen for first order, second order, up to third order we have seen. We know how to find the poles of first order, second order, up to third order. But beyond that, it's very difficult to find the roots of denominator, that is poles of the system. That's why it's difficult to say the location of poles. So there is a procedure to find the location of poles, whether it is on the right hand side or left hand side or on the j omega axis. For that, there is a criterion called Routh-Hurwitz criterion. Let us see that. Routh-Hurwitz criterion, some special cases are there. If you proceed the Routh-Hurwitz criterion, sometimes we may fail in the middle. There may be 2 reasons. One is the first column element may become 0 suddenly. If it becomes 0, you cannot proceed further because we have to divide by that number. You will get infinity. That's why you may not proceed further if first column element becomes 0. That is one difficulty. That is, we may have a 0 in the first column of a row. That is first difficulty. Second difficulty, sometimes may all elements in the entire row become 0. That is also possible. Then also not possible to proceed further. Let us see one by one. Let us see one by one. Let us now consider this sum. Example 3.5. Determine the stability of the system whose characteristic equation is this. That is, denominator polynomial of this system is this. So now we have to form the Routh array. What is the highest degree? s power 5. So we have to s power 5 and s power 4. 2 rows we can write. That is 1, 2, 3, 6, 5, 3. So in the first row we are writing 1, 3, 5. In the second row we are writing 2, 6 and 3. That's all. So first 2 rows we got. Now let us find S cube row. 2 multiplied by 3, you will get 6. That is Ath row, Bth row, Cth row. C1 equal to 6 minus 6 divided by 2. That is equal to 0. So you will get a 0. Then you see 2 multiplied by 5 minus 1 multiplied by 3. So what you will get? C2 equal to 2 10 minus 3 divided by 2. That is 7 by 3. 7 by 2. 7 by 2. So we cannot proceed further. You cannot find the S square row because we have to divide by this number. That's why we cannot proceed. Now, to proceed further, what we can do is, again, let us write the Cth row as, instead of 0, we will put epsilon. Epsilon and 7 by 2. So we are, in this case, epsilon tends to 0. Limiting case. That 0 is assumed as limiting case. Replace 0 by epsilon. That's all. Now we can proceed further. Now, what is dth row? That is a square row. Here, epsilon multiplied by 6. This we have to remove. So epsilon multiplied by 6. 6 epsilon minus 2 multiplied by 7 by 2. That is 7 divided by epsilon. 2 multiplied by 7 by 2. That is 6 epsilon minus 7 divided by epsilon. So S square. No further elements. Now we have to find the S power 1 row. S power 1. That is equal to, this is only one element. Here epsilon and 7 by 2 is there in this row. We have to use S3 row and S square row to find the S power 1. So each element we have to find. E1 equal to what? E1 equal to, we have to multiply 6 epsilon minus 7 divided by epsilon multiplied by 7 by 2. 7 by 2 minus epsilon multiplied by 0. Therefore 0 whole divided by 6 epsilon minus 7 divided by epsilon. You have to divide by this. That is equal to 7 by 2 only you will get. The same 7 by 2 you will get. Then S power 0 is what you will get. Here epsilon multiplied by one more element is there in S power 3. Epsilon multiplied by 3 minus 2 multiplied by 0. Therefore, you will get 3 here. 3 here. If you use this 7 by 2 and 3, you will get 3 here. You will get 3 here. So, what are the first column element? 1, 2, epsilon, then 6 epsilon minus 7 by epsilon, 7 by 2, 3. What are the first column elements? Let us write S power 5, S power 4, S power 3, S square, S power 1, S power 0. I'm going to write only first column. 1, 2, epsilon, 6 epsilon minus 7 divided by epsilon. S power 1 is 7 by 2 and 3. Now let epsilon tends to 0, you apply, what you will get? S power 5 is 1, S power 4 is 2, S power 3 is 0, S power 2 is, if you apply 0, minus 7 by 0, therefore minus infinity. Here 7 by 2, S power 1 is 7 by 2, S power 0 is 3. How many sign changes? No sign change, no change, no change. Here one sign change, here one sign change, here no sign change, no change. Only two sign changes, two sign changes. Therefore, two poles on the right hand side unstable. Unstable. Two poles on the right hand side, hence unstable. Now let us check in MATLAB. So roots, we have to enter the coefficients. The coefficients are 1, 2, 3, 6, 5, and 3. Only two roots have positive real part. Therefore, two roots on the right hand side. So what we found in Routh-Hurwitz is correct. Two poles on the right hand side, therefore unstable. Good morning to you all. Already we know that the poles, any one of the pole is on the right hand side of the S-plane, then the system is said to be unstable. We know. Already we have seen for first order, second order, up to third order we have seen. We know how to find the poles of first order, second order, up to third order. But beyond that, it's very difficult to find the roots of denominator, that is poles of the system. That's why it's difficult to say the location of poles. So there is a procedure to find the location of poles, whether it is on the right hand side or left hand side or on the j omega axis. For that, there is a criterion called Routh-Hurwitz criterion. Let us see that. Next is test the stability of the system whose characteristic equation is S cube plus 5s square plus 6s plus 30 equal to 0. Now let us form the Routh array. S cube, S square, mod and all 1, 5, 6, 30. Now S power 1 we have to form. 5 multiplied by 6, 30, A, B, C. Therefore, C1 equal to 30 minus 30 divided by 5 equal to 0. 0. So we cannot proceed further. But this is, we have to replace by epsilon or what we have to do? For that, we have to see the previous example. S power 1, how many elements are there? Only one element. Here, S power 1, how many elements? Only one element. Therefore, even though it is only one element, this is called row of zeros. Row of zeros. Even though it is one element, first column element is 0. So rule is we have to replace by epsilon. But if it is S power 1 means we have to consider it as a row of zeros. In that case, we have to form S power 1, we have to consider S square row. We have to consider S square row. That is auxiliary equation. That is called auxiliary equation. 5s square plus 30 equal to 0. So we have to differentiate this dAE by ds. We find that 10s plus 0, that is 10s. Therefore, s power 1 equal to 10. S power 1 equal to 10. That's all. S power 0 is what? S power 1 is 10. Therefore, 10 multiplied by 30 minus 5 multiplied by 0. Therefore, you will get 30 here again. 30 here. So, if we check the set of all first column elements, that is s cube, s square, s power 1, s power 0. What are the elements? 1, 5, 10, 30. No sign changes. No sign changes. Shall I tell stable system? No, we cannot say. Now itself. No sign changes. So here we have to consider the auxiliary equation. Auxiliary equation. Roots of auxiliary equation are roots of original equation. Original equation. What is the original equation? S cube plus 5s square plus 6s plus 30. Therefore, auxiliary equation roots are roots of original equation. What is the roots of this auxiliary equation? 5s square plus 30 equal to 0, or s square equal to 30 by 5, that is equal to minus 6. Therefore, s equal to plus or minus j root 6. The roots on the j omega axis. We know that if any of the poles on the j omega axis, it is marginally stable. Marginally stable. So therefore, the given system is not stable. It is marginally stable. It is marginally stable. So even though there is no sign changes, if auxiliary equation is there, we have to consider the auxiliary equation. The roots of auxiliary equation, any of the roots of the auxiliary equation is on the j omega axis, then it is not stable. It is marginally stable. Here, the roots of auxiliary equation is plus or minus j root 6. Therefore, it is marginally stable. Let us check what are the location of poles. Let us check in MATLAB. Now let us check by using MATLAB. MATLAB, we have to find the roots. The function call is roots. We have to pass the parameters, that is coefficients, that is 1, 5, 6, 30. Two poles on the j omega axis, 2.4, 2.4, two poles on the j omega axis. Real part is 0, only imaginary part. That's why it is on the j omega axis. What we found in Routh-Hurwitz is correct. Two poles on the j omega axis. Therefore, it is marginally stable. Marginally stable. Good morning to you all. Already we know that the poles, any one of the pole is on the right hand side of the S plane, then the system is said to be unstable. We know. Already we have seen for first order, second order, up to third order we have seen. We know how to find the poles of first order, second order, up to third order. But beyond that, it's very difficult to find the roots of denominator, that is poles of the system. That's why it's difficult to say the location of poles. So there is a procedure to find the location of poles, whether it is on the right hand side or left hand side or on the j omega axis. For that, there is a criterion called Routh-Hurwitz criterion. Let us see that. How many roots of the following polynomial are in the right of plane, left of plane, and on the j omega axis? That we have to find. Let us find by using Routh array. S power 5, S power 4, 1, 2, 2, 4, 1, 2. Now let us form MATLAB is there, Calzi is there. We can find the roots. Why we need this method to find? Because those days there is no Calzi, there is no software program to find the roots. So it is difficult to find lengthy procedure. That's why they found an alternate way. Now why we have to learn, you may ask? Because you cannot invent the wheel again and again. If you know this method, this can be implemented somewhere else. That is called research. That way we have to study all these things. So now we have to form S power 3. So 1 multiplied by 2 multiplied by 2 minus 1 multiplied by 4. That is 4 minus 4 divided by 2, that is 0. 2 multiplied by 1, then 1 multiplied by 2, again 0. So row of zeros. So what you will get is row of zeros. Therefore, we have to form the auxiliary equation. The auxiliary equation is equal to 2s power 4 plus 4s square plus 2 equal to 0. Therefore, dAE by ds equal to 8s cube plus 8s plus 0. Or we can write s cube plus s equal to 0. That is, the coefficients are s cube are 1, 1. Now we have to proceed further. S square. S square means what you will get? 4 minus 2. 2 by 1 is 2. Then 1 multiplied by 2 minus 0 divided by 1. Again 2 you will get. So s power 1 row. What you will get? 2 multiplied by 1, 2 minus 2, 0 you get. So again row of 0. Row of zeros. Already I told you that s power 1 means we have to consider row of zeros. Therefore, we have to second auxiliary equation. Second auxiliary equation is 2s square plus 2. Only even powers. Here also we have to consider only even powers. Because we have taken even coefficients only for that row. So here also we have to take even powers. Therefore, dAE by ds equal to 4s. Therefore, s power 1 is 4. S power 1 is 4. Then s power 0 is what is that? 4 multiplied by 2 minus 0 divided by 4, that is 2 you will get. So if you check the first column elements, if you check, write again s power 5, s power 4, s power 3, s power 2, s power 1, s power 0. What are the elements? 1, 2, 1, 2, 4, 2. No sign changes. No sign changes. No sign changes. But we cannot say the system is stable. Sometimes it may be unstable also. Let us check. Because it has auxiliary equation. What are the roots of auxiliary equation? Take this 2s square. Here, what are the roots of 2s power 4 plus 4s square plus 2 equal to 0. This can be written as s power 4 plus 2s square plus 1 equal to 0. Or we can substitute s square equal to x. Therefore, x square plus 2x plus 1 equal to 0. Or x plus 1 whole square. X plus 1 whole square equal to 0. Now x equal to what? S square. This implies s square plus 1 equal to 0, or s square equal to minus 1, or s equal to plus or minus j. S equal to plus or minus j. S square plus 1 whole square. S square plus 1 whole square. Therefore, the roots are s square minus 1 minus 1. Repeated. Therefore, s equal to plus or minus j. Again plus or minus j. So, if you plot this on the s plane, what you will get is plus j here, minus j is here, plus j is here, minus j is here. Sigma j omega s plane. But again plus j minus j. Therefore, repeated roots on the j omega axis. Repeated roots on the j omega axis. If repeated roots on the j omega axis means unstable, the repeated roots on the j omega axis means, this we have already seen, means unstable. So single pole is permitted, but repeated. Two poles on the same point on the j omega axis, therefore the system is unstable. Even though there is no sign change in the first column, it's unstable. So we have seen simple case, first column element equal to 0, then a row of 0. 3 cases we have seen. That's all. We have seen Routh array, how to find the roots on the right hand side by using Routh array. Already we have seen. Today we are going to see how we can fix the value of k so that the system is stable. We have seen that if you increase open loop gain k, there will be a movement of closed loop poles. As k increases from third order onwards, the closed loop pole will move to the right hand side of S plane. That's why we have to fix the value of k for the system to be stable. That we'll see today by using Routh-Hurwitz criterion. Using Routh-Hurwitz criterion, determine the stability of the closed loop systems that have the following characteristic equations. Characteristic equations means denominator polynomial of closed loop system. Determine the number of roots of each equation that are in the right of S plane on the j omega axis. How many poles on the right hand side? How many poles on the j omega axis we have to find. The first two sums you can solve yourself. 1139 1610. 3 minus 9 divided by 1. 3 minus 9 divided by 1. How much? Minus 6. 16 minus 10. 6 by 1. 16 minus 10. So, a square. What you will get? Minus 6 multiplied by 9 minus 6 multiplied by 1 upon minus 6. Minus 54 minus 6 divided by minus 6. Therefore, plus 6 plus 10 s power 1. So here this 10 will come here because 6 minus 6 multiplied by 10, 1 multiplied by 0 divided by minus 6, you will get the 10 here. S power 1 is 60 plus 60 because as per formula minus another minus 60. That's why you will get plus 60 divided by 10. Therefore, 120 divided by 10, that is equal to 12. So you are getting 12. Then you will get 10 automatically. Number of sign changes equal to number of sign change is equal to 2 because here one sign change, another sign change. Therefore, 2 sign changes. That's why number of poles, 2 poles on the right hand side, 2 poles on the right hand side, and the remaining 3 poles on the left hand side. 3 poles on the left hand side. So we got the same in MATLAB also. MATLAB also we got the same. The next sum is then let us check in the MATLAB. Denominator 1, 1. Tell me the coefficients. 3, 9, 6, 16, 10. If you put a semicolon, it won't echo. If you didn't put a semicolon, it will echo. Again, it will type the same. So that is the difference. If you didn't put the semicolon, no problem. But in C, if you didn't put semicolon, you will get syntax error. Almost like C, but some flexibility. So now we have to find the roots. For that, we have to pass the parameters. Roots. We are passing the denominator. How many? We have seen Routh-Array, how to find the roots on the right hand side by using Routh-Array. Already we have seen. Today we are going to see how we can fix the value of k so that the system is stable. We have seen that if you increase open loop gain k, there will be a movement of closed loop poles. As k increases from third order onwards, the closed loop pole will move to the right hand side of S plane. That's why we have to fix the value of k for the system to be stable. That we'll see today by using Routh-Hurwitz criterion. S power 4, S power 3, 1, 9, 4 minus 36 minus 32. So how many poles on the right hand side and on the j omega axis we have to find? S square. So minus 36 minus 36 minus of minus plus 36. Am I correct? So 72. How much? 8. 8 you will get. Then s power 1. Here you will get the minus 32. Automatically this will move here. This will move here. Then we have to find s power 1. 36 multiplied by 8 minus 32. So plus multiplied by 9 divided by 8. How much? Minus 36 plus 36. Therefore, you will get 0. S power 1 is 0. So s power 0 minus 32. So here you will replace this epsilon. Is it okay? No, because row of zeros. S power 1 means row of zeros. That's why we cannot proceed like this. We should not put epsilon if it is s power 1 row. So the auxiliary equation is 8s square minus 32 equal to 0, or s square minus 4 equal to 0, or s square equal to 4. That's why s equal to plus or minus 2. S equal to plus or minus 2. This is to find the roots for auxiliary equation. The auxiliary equation is 8 minus 32, or 1, 4. Auxiliary equation is this dAE by dt. ds equal to what? 2s plus 0. That is 2. So we have to replace by 2. So here automatically you will get minus 32. Because this 32 will come here. So how many sign changes? How many sign changes? Number of sign changes. Number of sign changes equal to 1. Because the last element is minus. Otherwise all plus. And the roots of auxiliary equation also, it is not on the j omega axis. Not on the j omega axis. Therefore, only one pole is on the right hand side. Number of poles on the RHS equal to 1. No poles on the j omega axis. 0 poles on the j omega axis. So let us check in MATLAB. Tell me the coefficients. 9, 4, minus 32, minus 36, minus 32. Only one root on the right hand side. 3 roots on the left hand side. No poles on the j omega axis. Even though the auxiliary equation is there, we cannot blindly believe that some roots on the j omega axis. That's why this sum. Sometimes the auxiliary equation may give poles on the j omega axis, may give repeated poles on the j omega axis. That's why it is important to see roots of auxiliary equation. Sometimes it may have poles on the j omega axis. Sometimes it may have repeated poles on the j omega axis. Sometimes it may not have any poles on the j omega axis. This sum is example for no poles on the j omega axis, even though we have auxiliary equation. That's why I solved this. We have seen Routh array, how to find roots on the right hand side by using Routh array. Already we have seen. Today we are going to see how we can fix the value of k so that the system is stable. We have seen that if you increase open loop gain k, there will be a movement of closed loop poles. As k increases from third order onwards, the closed loop pole will move to the right hand side of S plane. That's why we have to fix the value of k for the system to be stable. That we will see today by using Routh-Hurwitz criterion. Utilize Routh table to determine the number of roots of the following polynomial in the right half of S plane. Comment about the stability of the system. Comment about the stability of the system. S power 5, S power 4, 1, 2, 3, 6, 10, 15. So S power 3 rho is what? 6 minus 6 is 0. 20 minus 15, 5 by 2. 20 minus 15 divided by 2, that is 5 by 2, plus 5 by 2. Okay. S square is, here it is not row of 0. And S cube, only one element is 0. That's why we have to replace this by epsilon. So we are replacing this by epsilon. Now we have to find S square root. 6 epsilon minus 5 upon epsilon. So S power 1 is, so here we will get one more. This 15 will come here. S power 1 is 6 epsilon minus 5 divided by epsilon multiplied by 5 by 2 minus 15 epsilon whole divided by 6 epsilon minus 5 divided by epsilon. Okay. Let it be m. So m1 is, S power 1 is m. What is S power 0? S power 0 is automatically 15 will come here. This 15 will move like this. Alternate rows there. So because here 0, so what you will get here? Here 0, that's why m multiplied by 15 minus 0 divided by m equal to 15. So you will get 15 here. So now we have to replace epsilon as a limiting case. Epsilon tends to 0. Therefore, S power 5, S power 4, S power 3, S square, S power 1, and S power 0. 1, 2, epsilon. 1, 2, epsilon is 0. If you put epsilon equal to 0, what you will get? Minus 5 by epsilon, that's why minus infinity. Then m, for m, if you substitute, it becomes what? This is equal to epsilon LCM. If you take this epsilon getting cancelled, you will get 6 epsilon minus 5 multiplied by 5 by 2. Am I correct? 5 by 2 minus epsilon 15 epsilon square whole divided by 6 epsilon minus 5. Epsilon getting cancelled. So epsilon tends to 0 means this becomes 0. This also becomes 0. This also becomes 0. Minus 5. 25 by 2. This 5. So 5, this 5 also getting cancelled. Therefore, plus 5 by 2. Plus 5 by 2. Here, this is plus 5 by 2. S power 0 is 15. So, how many sign changes? Only 2 sign changes. Therefore, 2 poles on the right hand side. Comment on the stability. Comment on the stability, unstable system. The system is unstable. If it is asked in the examination, that's all. No need to find a number of poles on the right hand side, left hand side, geometric axis. But let us check here. How many poles on the right hand side? Tell me coefficients. 1, 2, 3, 6, 10, 15. Two poles on the right hand side. 3 poles on the left hand side. 3 poles on the left hand side. 2 poles on the right hand side. Only 2 poles having positive real part. Therefore, 2 poles. What we got here is correct. What we got here is correct. So 2 poles on the right hand side unstable. 3 poles on the left hand side. Take this. We have seen Routh-Hurwitz, how to find the roots on the right hand side by using Routh-Hurwitz. Already we have seen. Today we are going to see how we can fix the value of K so that the system is stable. We have seen that if you increase open loop gain K, there will be a movement of closed loop poles. As K increases from third order onwards, the closed loop pole will move to the right hand side of S plane. That's why we have to fix the value of K for the system to be stable. That we will see today by using Routh-Hurwitz criterion. This sum, second sum. Here, S power 5, S power 4, 1, 6, 15, 30, 44, 24, 44, 24. Find S power 3 minus 30 is 10, you know. Okay. 10 here, 40 is correct. 40. So S square is 300 minus 240, 60 divided by 10, 6. Am I correct? S power 1. S square 24 here you will get. So S power 1 is 240 minus 240 divided by 6, 0 you will get. So a row of zeros you will get. So we have to take this S square row. So 6 auxiliary equation is 6S square plus 24. So S square plus 4 equal to 0. So S equal to plus or minus J2. Poles on the geometric axis. Derivative of A by ds equal to 2S. That's all. Therefore, this can be replaced by 2. and s power 0 is 24. S power 0 is 24. So, no sign change. No sign change. But auxiliary equation is there. That's why we have to check the auxiliary equation. Auxiliary equation has two poles on the j omega axis, not repeated poles on the j omega axis, only two poles on the j omega axis. Therefore, what about stability? Marginally stable. Marginally stable. Marginally stable. It's marginally stable. Let us see more sums on range of k using Routh-Hurwitz criterion. S power 4, s cube, s square. 1, k, 1, 1, 1. What is s square? K minus 1. K minus 1 divided by k. K minus 1 divided by k. This 1 automatically will come here. S power 1 row, k minus 1 upon k minus k upon k minus 1 upon k. This is s power 1. S power 0 is 1. So this first column must be greater than 0. This column elements must be greater than 0. Therefore, this is already greater than 0. The condition is k must be greater than 0. K minus 1 upon k must be greater than 0 means k must be greater than 1. K must be greater than 0 as well as k must be greater than 1. If you consider this, k minus 1 upon k minus k should be greater than 0. Or k minus 1 minus k square. K minus 1 minus k square upon k must be greater than 0. Or k minus 1 minus should be k minus 1 should be greater than k square. So this is the second condition. The first condition is this is a subset of the second condition. That's why this we can ignore. If it is greater than 1, definitely it is greater than 0. That's why we need not consider the first condition. This can be ignored. This is the condition. K must be greater than 1. If k is greater than 1, it will not be satisfied. It will not be satisfied. Suppose 2. 2 minus 1, 1. 2 square, 4. Not satisfying. Even 1.1. If you put 1.1 minus 1 is 0.1. 0.1. Here 1.1 square greater than 1. So it is not satisfying. 1.1 square. It is not satisfying. Therefore, it's not possible to find a value which is greater than 1 and it satisfies the second condition. We cannot find a value of k such a way that it satisfies both first condition and second condition. Therefore, the system is unstable for any value of k. The system is unstable for any value of k. Unstable for any value of k or all values of k. Whatever may be the value of k, the system is unstable. So we cannot find a case to satisfy these two conditions together. This is second one. We have seen Routh array, how to find roots on the right hand side by using Routh array. Already we have seen. Today we are going to see how we can fix the value of k so that the system is stable. We have seen that if you increase open loop gain k, there will be a movement of closed loop poles. As k increases from third order onwards, the closed loop pole will move to the right hand side of S plane. That's why we have to fix the value of k for the system to be stable. That we will see today by using Routh-Hurwitz criterion. This is what we are going to see today. For each of the characteristic equation means what? Denominator polynomial of closed loop system. Then only we can call it as characteristic equation. Denominator polynomial of characteristic equation means denominator polynomial of closed loop system. Generally. Okay. Here, suppose I am having kg of s, I am having. That is open loop transfer function. Open loop transfer function is kg of s, or g of s equal to k upon s square plus 2s plus 3. Let us assume. What is closed loop transfer function? Let us assume this way. K upon s square plus 2s plus 2. T of s equal to T of s. Closed loop transfer function is what is unity feedback system. Unity feedback system means what is closed loop transfer function? Numerator divided by denominator plus numerator. That is equal to k upon s square plus 2s plus 3 plus k. Actually, in the open loop system, k is in the numerator. K is in the numerator. K is in the numerator. In the closed loop system, k becomes part of denominator. Suppose k is variable means the roots are moving. The roots are moving. As k varies, the roots are moving. How many roots you will get? This is second order, 2 roots. Suppose k varies from 0 to infinity. How many roots you will get? 2 sets of infinite roots you will get. 2 sets of infinite roots you will get. Because as k varied from 0 to infinity, as k equal to 0, you will get 1 set of roots. K equal to 1, you will get another set of roots. K equal to 2, you will get another set of roots. So, infinite number of roots you will get. That's why we have to fix k. Already I told you that from second order onwards, no problem. Up to second order, if it is open loop stable means closed loop also stable. We'll study later about that. From third order onwards, if it is third order system means as k increases, the poles will move towards the right hand side. This is what is the order of the system here? Fourth order. Third order onwards, as k increases, roots will move to the right hand side. Therefore, we cannot increase gain of the system beyond a certain value. If we increase gain, the system becomes unstable. The system becomes unstable. That's why the speed is dangerous. No system in the world is first order. No system in the world is second order. More than second order, all systems. Your bike you are riding means your order is third order onwards. Maybe third order. If you increase gain means the poles, the left hand side will move very close to j omega axis. So if any disturbance comes, you will oscillate. You can notice when the speed is very high, you cannot take decision. It will oscillate because the poles are very close to j omega axis. That's why speed is dangerous. Here, for what value of k, the poles are on the j omega axis, we can find by using Routh-Hurwitz. That we are going to find. What is the question now? The range of k for stability. I told you that the poles will move towards right hand side. Suppose this is a third order system. As k increases from 0 to infinity, this pole moves towards left. This pole moves towards right. This also moves towards right. So here k equal to 0. Here k tends to infinity. As k move, k tends to infinity. Here, for a particular value of k, the poles will be here. The poles will be on the j omega axis. For a particular value of k, the poles will be on the j omega axis. That value is called k max. Maximum value of k, up to which the system is stable. Below k max, the system is stable. If it is equal to k max, marginally stable. Above k max, unstable. So that we can find by using Routh-Hurwitz. That we are going to find. So the first sum is s power 4, s power 3, s square, s power 1, s power 0. The first row is 1, 25, 15, 20, k. Because they didn't give value. We have to find for what value of k the system is, range of k for which it is stable, we have to find. Therefore, it is k. Now, s square you have to find. What is that? 25 multiplied by 15 minus 20. How much? 375 minus 20. 375 minus 20 equal to, am I correct? 375? Okay. My 355 divided by 25, 5, 71. So 71 among 5. Here k will come automatically. S power 1th row, 71 by 5 multiplied by 20 minus 25k among 71 by 5. So we can write 71 multiplied by 20, how much? This is 71 by 5. $1,420 minus 125k divided by 71. S power 0 is k. So what are the first row elements? I am writing again first row elements only. S power 4, s cube, s square, s power 1, s power 0. First row elements are 1, 25, 71 bar 5, 1420 minus 125 k upon 71 k. So these are all must be positive for a stable system. These are all must be positive for a stable system. If all these elements are positive, it means what is the first condition? K must be greater than 0. K must be greater than 0. First condition. From s power 0th row, we can say that k must be greater than 0. And one more condition, 1420 minus 125k should be greater than 0, or k should be less than 1420 divided by 125. K must be, so 1420 greater than 125k. Therefore, k must be how much? How much? 1420 upon 125, how much? 11.36. So, this, if k is greater than, if k is greater than 11.36, then only, sorry, if k is less than 11.36 and k is greater than 0, then only the poles will be left hand side. Otherwise, it will be on the right hand side. If it is equal to 11.36, poles will be exactly on the j omega axis. Poles will be exactly on the j omega axis. If it is exactly on 11.36, can you tell more the decimal places? 11.36. Very good. So k should be the range of k. It is asked. Range of k is it should be less than 11.36 and it should be greater than 0. For 0 to 11.36, the system is stable. At k equal to 11.36, it is marginally stable. Marginally stable. Marginally stable. When at 11.36, if it is greater than 11.36, the system is unstable. Let us check all these things in MATLAB. So let us put 11.36 exactly and check. Tell me the coefficients. 1, 125, 15, 20, 20, k equal to 11.36. 11.36. We cannot, or we can enter k. That is also possible. We can vary k. That is also possible. K equal to 11.36. Now let us check the roots. 2 poles on the j omega axis. 2 poles on the j omega axis. So the closed loop system, it becomes marginally stable for 11.36. Let us check for k equal to 11. Let us check k equal to 11. 11 k equal to we have to run this one time. We have to run this one time. Now we can find the roots. All poles in the left hand side. All poles in the left hand side. Now let us check the simulation of what happens when k equal to 11.36. K equal to 11.36 transfer function. Numerator. Is it the transfer function? K equal to 11.36 and we have to run one time. We have to find the transfer function. Okay, 11 numerator whatever. 11.36. Transfer function is 11.36 s power 4 plus 25 s cube plus 15 s square plus 25 s 11.36. So for this, let us check the response. Impulse response of C. Sustained oscillation. Sustained, no change in amplitude. Remains oscillating up to 800. Let us give less than 11. Less than 11. K equal to 11. 11 point, less than 11.36. What happens? Let us check. We have to run numerator. It becomes 11. Denominator also we have to run. Now we have to find the transfer function. transfer function. Now K value is less than 11.36. Now what happens to impulse response? Oscillating and finally settle. Oscillating and finally settle. Let us see more sums on range of K using Routh-Hurwitz criteria. Third one, S cube, S square. 1, 3K, K plus 2, 4. So what you will get, S power 1 is 3K multiplied by K plus 2 minus 4 upon 3K upon 3K. S power 0, you will get a 4. So what are the conditions? So for a stable system, the first column elements must be greater than 0. For no sign change, the first element is positive. Therefore, all the remaining elements also must be positive. Therefore, 3K must be greater than 0. Therefore, K must be greater than 0. K must be greater than 0. First condition. This is the first condition. Second condition we can get from here. 3K square plus 6K minus 4 should be greater than 0. 3K square plus 6K minus 4 should be greater than 0. Or we can say that K square plus 2K minus 4 by 3. 4 by 3, 1.33 greater than 0. The roots are K equal to minus 2.527 and minus 0.527. Therefore, we can factorize this as K plus 2.527 and K minus 0.527 should be greater than 0. So the K must be, what should be the value of K? K should be greater than 0.527. Greater than 0.527. One condition is K must be greater than 0. The second condition is K must be greater than 0.527. So if it satisfies, automatically this will be satisfied. Therefore, we can ignore this condition. You can consider this alone. K must be greater than 0.527. K must be greater than 0.527 alone can be considered. Because automatically this will be satisfied. Automatically this will be satisfied. So the second condition is satisfied, then automatically first condition will be satisfied. Therefore, if K equal to 0.527, then what you will get is, you will get sustained oscillation. Because rho of 0 you will get, if K equal to 0.527 means, you will get a rho of 0. S power 1 rho becomes 0. If S equal to 0.527, if you substitute here, this becomes 0. This becomes 0. It means rho of 0. Therefore, this becomes auxiliary equation. So we can find the roots on the j-omega axis by using that. Are you able to follow? If S power 1 rho becomes 0 means, for what value this becomes 0? The factorized value is 0.527. Therefore, when k equal to 0.527, this becomes 0. That is S power 1 rho becomes 0. It is important point you consider. S power 1 rho becomes 0. Only one element is there in S power 1. Therefore, row of zeros. Therefore, S square rho becomes auxiliary equation. Auxiliary equation means we can find the poles on the j-omega axis. Therefore, substitute k value in the S square rho. Consider S square rho. Take S square rho and substitute k value. 3 times 0.527. 527 plus 4. S square plus 4 equal to 0. If you substitute that, what you will get is S square equal to minus 4 upon 3.527. If you substitute this, if you find S, that is j omega equal to S equal to plus or minus j 1.59. So the poles on the j omega axis. What is S plane? This is S plane. This is S plane. This is sigma. This is j omega. Omega means what? Frequency. Omega means frequency. Frequency is 1.59. Therefore, the frequency of oscillation, the question it is asked, the question, find the frequency of oscillation. Determine the value of k so that the system is marginally stable and find the frequency of oscillation. Determine the value of k so that the system is marginally stable. The first sum, 11.36 we got. In the second sum, for none of the values, the system is stable. For the third sum, when k is equal to 0.527, it exhibits sustained oscillation. Poles are on the j-omega axis. What is the frequency of oscillation? 1.59 radians per second. 1.59 radians per second. We can find the frequency of oscillation. Have you understand this? Let us see more sums on range of k using Routh-Hurwitz criteria. S power 4 S cube 1 k 5 10 10k S square equal to 5k minus 10 upon k, and 10k will come here. S power 1 5k minus 10 upon k multiplied by 10 minus 10k square upon 5k minus 10 upon k. S power 0 is 10k. So what are the conditions? The conditions are, the first condition is k must be greater than 0. K must be greater than 0. The second condition is 5k minus 10 upon k must be greater than 0 means 5k must be greater than 10 or k must be greater than 10 by 5. Therefore, k must be greater than 2. If it is greater than 2 means automatically it will be greater than 0. That's why this condition can be ignored. This is first condition. K must be greater than 2. Second condition, from S power 1 row we can get 5k minus 10 upon k multiplied by 10 minus 10k square must be greater than 0. Or we can say that 5k minus 10 multiplied by 10 minus 10k cube must be greater than 0. Or okay. So 5k, 10 is getting cancelled. 5k minus 10 minus k cube must be greater than 0, or minus 5k plus 10 plus k cube must be less than 0. If you do roots of these are one of the roots equal to one of the roots is equal to 2 minus 2.9055. Therefore, we can do synthetic division and and it can be written as, this polynomial can be written as k plus 2.9055, and if you do synthetic division you will get k square minus 2.9055k plus 3.442 should be less than 0. So already we got one condition, k must be greater than 2. K must be less than minus 2.9055. K must be less than. If you put less than, say 3. If you put 3, this becomes negative. Minus 3, if you put here, this becomes negative. If you put minus 3, this becomes positive. This is also positive. Therefore, always this is positive for negative values of k. This is always positive. This is negative, will be less than 0. Therefore, k must be less than minus 2.9055. So the first condition is k must be greater than 2. Second condition is it must be less than minus 2.9055. It is not possible to satisfy both conditions. One condition is k must be greater than 2. Another condition is k must be less than minus 2.9055. It is not possible to satisfy both conditions. Therefore, for all values of k, k unstable. It is not possible to satisfy both conditions. Find the range of k to keep the system shown in figure to be stable. So we would find the k value. This is a closed loop system, negative feedback, h of s equal to s minus 1 upon s square plus 2s plus 1. G of s equal to k upon s. Therefore, closed loop transfer function T of s equal to the closed loop transfer function is 1 plus g of s h of s k upon s multiplied by s minus 1 upon s square plus 2s plus 1. That is equal to k upon s whole divided by s
multiplied by s square plus 2s plus 1 plus k multiplied by s minus 1 whole divided by s multiplied by s square plus 2s plus 1. This is getting cancelled. Therefore, k s square plus 2s plus 1 upon s cube plus 2s square plus s plus ks minus k, that is equal to k multiplied by s square plus 2s plus 1 s cube plus 2s square plus 1 plus k multiplied by s minus k. So the characteristic polynomial is denominator is the characteristic polynomial. So this is the characteristic polynomial. This is the characteristic polynomial. The roots of that characteristic polynomial must be on the left hand side for stable system. So now we will apply Routh-Array. We got the denominator polynomial. For that s cube. So we have to form the Routh-Array s cube s square 1 2 1 plus k minus k. S power 1 is 2 multiplied by 1 plus k minus of minus plus k divided by 2. That is so this becomes s power 0 is k minus k. Therefore, this column must be positive. All elements in the column must be positive. That's why if we take this minus k should be greater than 0 or k should be less than 0. That is the first condition. K must be less than 0. If you consider this 2k plus 2 plus k divided by 2 must be greater than 0, or 3k plus 2 must be greater than 0, or k must be greater than minus 2 by 3. So the value is lies in between 0 and minus 3 by 2. The k value must be 0 and minus 2 by 3. The range of k for which the system is stable is minus 3 by 2 to 0. If it is in this range, then the system will be stable. System will be stable. To make s power 1 equal to 0, what you will get? If you equate 3k plus 2 equal to 0 means k equal to minus 2 by 3. So for minus 2 by 3, it will exhibit sustained oscillation. Minus 2 by 3, it will exhibit sustained oscillation. Minus 2 by 3, it will exhibit sustained oscillation. If you want to find the frequency of response, you have to use s square 2s square minus k equal to what? 2 by 3 minus 2 by 3 equal to 0, or s square plus 2 by 3 equal to 0, s equal to plus or minus 1 by 3 square root of 1 by 3, or that is equal to j 1 by 3. S equal to plus or minus j 1 by root 3 plus or minus j 1 by root 3. That is the frequency of oscillation.
here when 70, this row, s power 1 row will become 0 when k equal to 11.36. Therefore, we have to consider s square row. S square row is what? S square row is 71. S square row is 71 by 5 s square plus 11.36 equal to 0, or 71 bar 5 s square equal to minus 11.36, or s square equal to minus 11.36 multiplied by 5 divided by 71. Therefore, s equal to plus or minus j square root of 11.36 multiplied by 5 upon 71. That is equal to plus or minus j 0.894. The frequency of oscillation is 0.894 for the first sum. For what value of k the system is marginally stable, and find the frequency of sustained oscillation. To find frequency of sustained oscillation, what we have to do is make s power 1 row 0. For that, what is the value of k? You have to find. So you will get a row of 0. If you make s1 row equal to 0 means a row of 0. So consider the auxiliary equation s square row, find omega. That's all. That is the procedure to find poles on the j omega axis. Poles on the j omega axis. The omega value is 0.894.